This diagram depicts what's going on in the question. So as you can see, you have your optical axis and then you have your lens sitting in the center of the axis. So right here. And then we have light rays coming from our object P hitting the edge of the lens and then passing through the lens to form an image P prime on the face of our optic fiber. And as you can see here, we have our optic fiber with the cladding and the core to prevent light from escaping, and so light can undergo total internal reflection within the optic fiber. And you also have light rays from point P prime, the image, undergoing total internal reflection, as you can see here, and that will continue through the fiber. And so back to the lens, the distance from the lens to our image, which we were given, is d prime, 2.33 millimeters, and we are trying to find our radius here. So if we look carefully, we can see that this whole area here forms a right angle triangle, and we can use the formula tan theta 1, where this is our theta 1, equals opposite over adjacent. And so if we look here, our opposite would be the radius, which we're trying to find, and our adjacent would be the distance, 2.33 millimeters. So here we'd have tan theta 1 equals opposite our radius and our adjacent d prime. So if we multiplied here to isolate for radius, we'd get that our radius is actually equal to tan theta 1 times d prime. So if we had theta 1, we'd be able to solve for our radius. So now this might be an area of difficulty for students to understand how to find theta 1, but if we look carefully here, we can see that we're switching mediums. So we are going from air into our core, and whenever we switch mediums, the formula to find angles is our Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. So this is a key step, because if we know n1 for the air is just 1 and n2 for the core is the cladding, we can find theta 1 if we know theta 2. So now is also a key step, and it can be an area of difficulty to understand how to find this theta 2. But if we look closely here, we can see that this ray actually makes a right angle triangle here. So in this right angle triangle, you have your 90-degree angle and your critical angle and your theta 2. And what we know about right angle triangles is that all angles will have to equal to 180. So your 90 degrees, your A and your B have to equal 180. And if we replicate that, just here, our A would be theta 2 and our B would be theta critical. And so if we can find theta critical, we can find theta 2, and then we can find theta 1. So the formula for finding theta critical is actually theta critical equals sine inverse n2 over n1. Now this is a key step, because with all our n's, we might be getting confused, but we need to focus on where we are. So we're within this core cladding here, within this optic fiber. So light rays are traveling through the core, and they're trying to reflect through the cladding, but they're getting totally internally reflected. So our n1, our incident ray, is within the core, and our n2, the refracted ray, which we don't really see here, but that would be through our cladding. So our n1 is the core, which is 1.65, and the cladding is n2, which is 1.55 for the indexes of refraction. So if we put that all into our formula, we can see that theta critical is equal to sine inverse of 1.55 over 1.65, which would be 69.95 degrees. And here we can see that it's also important for n1 to be greater than n2 in order for total internal reflection to occur, which is one of the significances of this question, understanding total internal reflection. So now we have theta critical. Back to our right angle triangle, we can substitute our theta critical for 69.95 degrees. And if we know that 90 degrees plus our theta critical plus theta 2 equals 180 degrees, we'd add these two together and we'd see that 159.95 degrees plus theta 2 equals 180. And so subtract by 159.95 degrees from both sides in order to isolate theta 2. We'd see that theta 2 is 20.05 degrees. So now we have our theta 2, we can go back to our Snell's law equation. And N1, as we said before, was 1. And our N2, as we said before, was 1.65. And now we have theta 2. So 1 sine theta 1, which we're looking for, 1.65 times sine 20.05. If we multiply all this together, we get that sine theta 1 equals 0.57, where 1 times sine theta 1 is just sine theta 1. And then in order to find theta 1, which is what we're looking for, so that we can find our radius here, we need to do sine inverse of 0.57, and then we'd get that 34.45 equals to theta 1. So now we have our theta 1. We can go back to our radius equation. So the radius is tan theta 1 times d prime. So our radius is going to be tan theta 1 times d prime, which is 2.33 millimeters. And then we get our radius is 1.6 millimeters, which would be the radius of the lens here. It's also important to note that these two angles are not equal, because as you're going from different mediums, your incident ray is actually going to bend towards the normal line here, because N2 of the core is a lot greater than N1 of the air, so your light rays will bend towards the normal line, which is also the optic axis here. So that's why these two angles are not the same, and an area of difficulty may be understanding that, so that you don't get the wrong answer for theta 1 and then for your radius. Significance of this question is that we were able to understand total internal reflection within optic fibers, and one of the most important modern applications of total internal reflection is the optic fiber. So it's definitely an important concept. We were able to see how light rays have to be straight and they can form images using a lens. We were able to also understand how light rays refract as they go through different mediums, and how we can use Snell's law to find the angles involved, and then also relating that to properties of the lens, such as the radius. And so, thank you.